Looks like you also got sick.
Yeah, it's the allergy.
Oh, it's just allergy, not COVID, right?
No, not used to the weather here.
Oh,
As
long as it's not COVID, you're fine. Yeah, yesterday that day we talked a little bit about the paper. So I don't know whether he will post the video. You can see. Basically, I asked students to write about 5 to 6 pages, maybe with some references. And the important thing is to somehow have some concept you learn in this class in that paper, maybe some equations or some theory. Yeah. So I'll give you the very last homework. So today, yeah. So that will be the last one. So after this one, I think these are more like some concepts, because this theory of these subjects are very difficult. So
can you explain a little bit about last homework?
Which one? Yeah. So
Square lattice.
yeah, actually that's a very straightforward calculation. Just the example we did.
Yeah.
Remember I asked you to go from here to here and from here to here, right?
Yeah.
When you go from, this is your kx, ky.
Yeah.
If you go in this direction, we know your ky is 0, right?
0, yeah.
So you have only kx, so that goes from 0 to this pi over a, right?
Yeah.
So kx go from 0 to y. Then when you do the empty lattice approximation, that's basically, yeah. So this is g minus your this k, yeah. So square. So when you take this one, so this is basically your h, whatever k l. This one, right? Then you have to subtract your k value, but those k values are basically, in this case, actually no c, right? You only have h minus your k x, right? Kx squared plus, then other one is basically ky is 0, right? This one. So now just use kx from 0 to, so any number, right, from here. Then pick any h and k. So it can be 0, 0 or 0, 1, anything like that. So then when you go from here to here, what do you have? Your kx is fixed, right?
Yeah.
That is pi over a. Then ky goes from 0 to pi over a, right? So then you have another one. Let's pick only few branches where h and k, pick maybe 0, 1, maybe 1, 0, something like that. Then you get these curves, right? That's it. So what you are going to do is, this is your gamma point, gamma to, you go to L point, x point, right? X, then from x point to L point. So from here to here means you are doing this one, kx only. Kx changes, ky 0, right? Then you get some kind of curve, maybe something like that, right? So then when you go from x to L, so then you have some equations or something like that. Just follow the same thing I did for the 3-dimensional case.
Yeah.
But here it's easy, right? From here to here, you have to just put some numbers for your x value. So that's what I did, right, in that example. But there I said it is x minus x. So x goes from, so say 0.1, 0.2, 0.3, like that. So that's it. So in this curve, kx changes and ky is 0. In this case, your kx is constant, then ky changes. That's it. I don't want you to draw so many branches. Just with maybe 3 or 4. Can be 0, 0, 0, 1, 1, 0, things like that. Then you will see some maybe something like that. So different colors. Just try that. I think that's what I want people to. Is that clear?
Second one is type 1.
Yeah, that's very simple, right? Yeah.
Doing in the class.
Yeah, so the same. Yeah, so when you do this one, you will find you have to add all these E, I, K, X. You have some here, right? So only thing you have to now do is X go from, if it is
Second.
the first order we already did, right? So you have, so whatever this times X plus A and minus A, right? That's why you get dikx minus E minus ikx divided by 2 the sign and something. If you go to second one, what you get? This becomes 2A, right? 2A and minus 2. Then you get something plus some cosine KA plus, with this one you get cosine 2K kind of thing, right? So in the class only I considered the nearest neighbor interaction. That means I only considered one. This is A, other one is minus A. That's why we got the cosine term, right? So then if you go to the next one, you get, this means IK 2A. Then this side you have IK minus 2K. What is this one? Cosine 2K. Right? So if you look at your Venn diagram, cosine means like this. Now what do you get? You get another term, then you get something like this. That's how the band structure should look like. This is what you had with only first term, right? Just plot and see, you get another. So like this. This is coming from the cosine Ka, this is coming from the cosine 2K.
Thank you.
Yeah. Just try, that's all I want in the homework. I want people to try. Otherwise you can go and find the solutions anyway. Yeah. I want students to try it. Unless you do yourself, you will never learn. That's the thing, right? I think today not many people here because Jacob is in a conference and Israng is getting ready for the qualifying and he's also ready for the qualifying. Yeah. Okay, so today let's talk about superconductivity. So we'll do about 2 or 3 classes. Actually, yeah, that's another thing. So we have next week, Tuesday, Thursday, and the following week only Tuesday, right? Then we have the Thanksgiving break. So then after that we have only 2 days, right? That's it. Then the semester is over. So maybe during this Thanksgiving break you can start working on your paper, right?
Yeah.
Otherwise, yeah. So I will give you one last homework, maybe only 2 problems. So on the superconductors and devices. So that you can turn in around this time or whatever. Yeah. That's the last homework anyway. So that means today and today we are here, right? So then next week we will finish superconductivity. Yeah, then we have Tuesday class here. I don't know whether you guys are going to be here that Thanksgiving week?
I won't, I will be leaving.
You will be, yeah.
Next week.
Okay, I know a lot of people to go out. Maybe if you want, we can cancel Tuesday's class because a lot of people they are out of town, right? So, in the past, I to cancel because we had the physics Thanksgiving party. So during this time, 12 o'clock, right? So let's cancel that week. So we will have next week 2 days.
Yeah.
Then after Thanksgiving 2 more days. Yeah, let's try to finish superconductivity. Then we'll have the magnetism in the last 2 classes. Yeah, this actually today's class mostly first part I'm going to talk about some history of superconductivity, right? This is really fascinating area, but it took lot of time, actually long time to come up with the theory how to explain the superconductivity, because everything we learn, right, it's all electrons, holes and phonons, right? So we cannot explain the superconductivity with one phenomenon. So we need to combine all these things together to come up with some new kind of particles and some quasi-particles and things like that. So in this class mostly I will talk initially about normal state. Before it becomes superconducting, we call this a normal state, right? So then there's something called the critical temperature. Below that critical temperature it becomes superconductor. That's basically a phase transition, right? From normal state to superconducting state. That's why this is really interesting for people working in the quantum computing, because you need qubits, right? So basically you need to have 0 and 1 state, but you should be able to make superposition of these states, right? So that's why, because if you take your normal state as some state like psi n, quantum state, then you can have psi superconducting state as another state, right? So this is like 0 and 1, but in typical electronics we have zeros and ones, binary, that's all, right? But in this quantum state you can have another state with any linear combination of these 2 states, right? That means not just binaries, you can have many states. So that's why you need to have well-defined 2 states. It can be normal superconducting or maybe paramagnetic to ferromagnetic, and some kind of very well defined 2 states. So that's why superconductivity is really interesting in quantum computing. But the bad thing is you need to use very low temperatures, right? So first, hallmark of superconductivity. If you have found a superconductor, you need to make sure all these things are, I don't know, we heard recently people came up with this room temperature superconductor. So they even showed some kind of levitation. This was this, but you are working on this copper phosphide, then we added some another material. So they said it's a superconductor because it went to very sharp resistance change, but later found out it's not a superconductor. If you have a real superconductor, these 3 should be satisfied. Your resistance should go to perfectly to 0, then it should be perfect diamagnetism. That means the susceptibility should be -1. So this diamagnetism means if you have some magnetization, that's depending on your chi times your applied field, right? So this, if it is chi is positive number, we say it is a paramagnetic. If it is a negative number, is a diamagnetic. Diamagnetism chi is a very small number. But superconductors, they are perfect diamagnetism. That means chi is -1. That means there's no magnetic field inside the superconductor. That's the important thing. Say if I have a superconductor, if I apply some external magnetic field, then you have this opposing diamagnetic means opposing magnetic moment, right? So this M is exactly equal to -h because this is -1, right? Then what is the total B?
Inside.
0, right? Because this H and M exactly equal. That's why it's a perfect diamagnetism. Next thing is this flux quantization. If we have a superconductor, suppose it's a kind of ring. If you have a magnetic field, the flux, you know how to calculate the flux, right? What is the flux? Flux is basically this one, right? So if it's a superconductor, this flux should be the quantized some quantity called this unit, the flux value. So this n goes from 1, 2, 3 like a quantized value. So that's called a flux quantization. We'll talk about all these things. So unless you can show all these three are satisfied, you cannot prove you have a real good superconductor. So then to explain the superconductivity, like I said, people worked very hard to come up with the theory. So initially, these London brothers, they came up with some theory. Still it is valid, pretty good theory. Then actually Landau Ginzburg, so this Russian scientist, actually Ginzburg, he once visited UK, University of Kentucky, so we went to meet him. So they came up with this some phenomenological theory. So explaining this something called the penetration depth and the coherence length. So then very recently there is a new kind of superconductor we call is the traditional superconductors we call type 1 superconductors. So then this new we call the high TC superconductors, they are type 2 superconductors. So sometimes we call this the dirty superconductors. So they are. So then actually real science actually came after they developed something called the BCS theory. So Bardeen, Cooper and Schrieffer, these three scientists, so they came up with this theory. Actually Bardeen is the graduate advisor of Schrieffer. He was the graduate student, so he was his advisor. Then Cooper was the postdoc in the group. So they came up with this theory. Also, do you know anybody special about Bardeen? He's the only one who has got 2 Nobel Prizes. One on this BCS theory, other one is for the transistor, right? Transistor, Shockley and Bardeen. So these are smart people. So here, this is what I said about the resistivity. If you measure the resistance as a function of temperature, you have something we call the normal state. Then immediately it goes to perfect zero. Then resistance becomes zero below this special critical temperature called TC. That's the critical temperature. So then if you look at the magnetic induction, so magnetic induction means this B value. So above TC, before it becomes superconductors, then your B is basically mu naught, then B minus M, right? So but M is basically, H minus M. That's the total, right? So typically M is, I can say chi times H, right? That's how we define susceptibility. This is mu 0 H 1 minus chi. So you can see if chi is very small, so then B is almost mu 0 H, right? But if chi is exactly 1 in negative terms, so then B becomes 0, right? So that means if you look at the magnetic induction, you can see B becomes 0 here, but here you have finite value, right? Because chi is small value. That's what you have here. So how does it look like if you draw M versus M is the magnetization, right? Versus H, or B versus H. So B we already showed, right? How does B looks like? B 0 here, right? At Tc, then whatever here it is, this is normal state, right? How does the M looks like? Can somebody tell me? So M is high H, right? So if it is below Tc, M should be minus H. That means something like this, right? If I plot minus M, it looks like this. But M equals H, right? M equals chi is minus 1 means M is minus H. It looks like this, right? So then at this point what happens? M becomes, but this is really small, so that means it's almost 0. This is how it looks like M, and this is how it looks like B. Inside, below Tc, your B is 0, right? M is minus H. So, try to understand. This is the magnetic flux is given by total flux is actually this quantized value n equal 1, 2, 3, 4 like that. Sometimes we call this is Josephson effect. So this is the first time this Kremlin honors, he discovered the superconductivity. So he was measuring the resistance of mercury. So I think few months before that he liquefied helium. So helium has boiling point of 4 Kelvin, right? So before that you didn't have access to any low temperatures, but on us he liquefied helium, then he was measuring the resistance as a function of temperature. Actually his student was, this is an interesting story, his student was doing the experiment in the lab in the night. So when he was doing, actually they were using, I don't know whether you're familiar with something called the Wheatstone bridge. So basically you have to change that length and make your current 0. So when he was doing that, so at this temperature his resistance went to 0. So then immediately he called from the lab to honors and said, I saw this interesting phenomena. Then he said, oh, you must have shorted your Wheatstone bridge. So then next day, even the student didn't know, he just, I think, advertised and publicized these results. Still nobody knows the name of that student. So that's where he found the superconductivity of mercury. You can see that become, your Tc is about 4.2. These are real data points taken by that student. So then to explain this superconductivity, so they came up with this theory. Like I said, you cannot explain in terms of electrons. So they actually, this BCS Cooper, he came up with this idea. What happens is below this low temperature, the electrons, typically electrons have negative charges, right? You cannot have these two together where they try to repel, right? But for some magical reason, these electrons, they come as a pair. They call the Cooper pair. So how can you have these two electrons coming together? Because electrons have negative charges, right? They should repel. Actually, the way they try to explain is, because these electrons are in your material, right? So these are electrons coming from your atoms. So then you have your lattice. In the lattice, you have this positive ions, right? So when this Cooper pair is coming, actually these are not that close to each other, about some nanometer apart. So these electrons in the Cooper pair, they have opposite spins, also opposite momenta. That means if this one has velocity v or momentum, this one has velocity minus v. So when this one, suppose this Cooper pair is moving in your lattice, so when it is at certain point, because of this first electron in the Cooper pair, so that perturbs the lattice, because lattice has positive charges, right? They attract lot of these positive charges towards the Cooper pair. Then that the lattice becomes polarized, right? It's more positive. So then you have that positive charge and this Cooper pair attraction, right? So here you have repulsion, but you have the lattice and Cooper pair attraction. So that attraction force is stronger than the repulsive force. So that will keep the Cooper pair together. So that means there's some energy you need to have to keep the two electrons together. So that energy should be called delta. If your energy is much higher, suppose high temperature, so that is too large to separate the two electrons. If you separate, you don't have superconductivity anymore, right? That's why you need to have low enough temperature to keep the two electrons together because of the polarization of your the lattice. So that more charge, positive charges are there, they will attract. That means basically it's a electron-phonon interaction, right? This positive charges mean these are coming from the phonons, right? Phonon, electron-phonon interaction. Superconductivity is a result of electron-phonon interaction. That's why I am showing here. So at low enough temperature, these Cooper pairs are like this. So actually, also these Cooper pairs are bosons, because your spin is 1, right, or 0. It can be, you have two spins, right? So it can have 0 or 1. So that means that's a boson. Boson means you can have any number of particles in a given state, right? So fermions, you need to obey the Pauli exclusion principle. So that's why these Cooper pairs are at this lowest state here. It's more like condensed phase here, right? It's more like the super fluidity, right? So also the Bose-Einstein condensation. So same thing, because it is helium-4. So they can condense into one single energy state. But if your energy is higher, what happens? Higher than this delta, this Cooper pair will dissociate. Then you can have some electrons we usually call the quasi-particles. So they can be here or maybe in the quasi-whole state. But low enough temperature, they always stay in this one. So this is the energy required to break apart the Cooper pair. Here I'm showing here 0. So this, then at high enough temperature you have some particles here or some particles in this side. So this is a very not easy theory to work with. So then also when you talk about superconductivity, I said inside the superconductor your magnetic field is 0, right? That means if I have this superconductor, if I have the external magnetic field, it cannot go through here. Then the only thing can happen is it should go around, right? So that's why if you have a superconductor, your magnetic field doesn't penetrate through, it will go over the superconductor. If it is above TC, it will penetrate through, then you have magnetization here, right? So, but if it is below TC, usually happens this one. But important thing is, if you have this superconductor, suppose this is your superconductor, this magnetic field, if I draw inside magnet, so with the distance here, x. Inside the suppose your magnetic field is something like this. So it doesn't go to 0 immediately. I said you have h here, right? So inside here, it becomes 0 magnetic field, but it doesn't go to 0 immediately. There is some depth, we call the penetration depth. Through that penetration depth, it goes to 0. That means if I have magnetic field, suppose at this point you have magnetic field here. So then that magnetic field is gradually decreasing and goes to zero. Suppose this is my zeroth one. It goes to zero at some distance. We call this distance lambda, this penetration depth. Because it doesn't go to zero at this point. It goes to, that means actually your H is something like outside magnetic field times exponential minus H over lambda. We call the penetration. Exponentially it is going. Exactly. So it doesn't, at the surface it is not going to be zero. It has to go a little bit inside the, so suppose this is, this one. It goes to zero after certain distance. Here you can see here, this is outside magnetic field, then inside magnetic field goes to zero over this distance. So if you show this one, you can see inside this length, it is non-zero. It's gradually decreasing, but it's only go to zero at this penetration depth. Is that clear? So then also if you look at this penetration depth as a function of lambda, so as a function of temperature, this is your lambda as a T. So this is temperature dependence of your this lambda, because we are talking about temperatures above Tc and below Tc, right? So typically at this is T equals 0, that means lowest temperature, we call lambda 0. So then my Tc is somewhere here. If you look at this lambda, actually it is showing this kind of here. You can find this lambda T goes something like, so lambda this 0 temperature value divided by 1 minus T over Tc to the power 4. This kind of relationship it shows. Here you can see how lambda T changes. At Tc it becomes very large, right? So then you can see how this perfect diamagnetism, sometimes we call this the Meissner effect. So that's the reason. Have anybody seen this demonstration? No? Oh geez, I should have. I have it in 351 lab. If you take a magnet and this high Tc superconductor, so if I cool it below Tc, you will see that magnet is floating. It's we call the levitation, right? So that's because of this phenomenon. It's more like a cushion in here. Or you can think about if I have superconductor, if I have this magnet here, you have like an image magnet here that is repelling this magnet. So there are a lot of interest to use this levitation to make this called this levitation trains, right? If you can make your railway track with superconducting material, you can make it to float. That way it doesn't make physical contact, right? So it can be floating, so that means it can be as fast as possible. Actually, you can show even with these magnets. If you have several magnets, if you put this superconductor, it will go around this one without touching the magnet. This lev train, that's a levitation train. So then, actually, the superconductivity, one thing we know it is the temperature, right? So if your temperature is low, you have the superconductivity. If it is high, no superconductivity, right? Also, the magnetic field can kill the superconductivity. So typically, if you have any magnetic field more than something called the critical magnetic field, if your magnetic field is larger than certain critical field, you lose the superconductivity. So here in this range you have superconductivity, but if you have, your magnetic field is much higher, you don't have that one. So then another thing is the current. So if you pass a current through your superconductor, right? So if your current is higher than certain critical value, you lose the superconductivity. So you can see within this range you have superconductivity. If your current is above this one, you don't have superconductivity. That's three things you have to be careful. One is your T that we know, right? T has to be less than Tc. Your magnetic field, external magnetic field should be less than your critical field. Then your current also should be less than your critical current. If they are above these values, you lose your superconductivity. So, like I said, like in 1985 or something, they found this something called high Tc superconductors or type 2 superconductors. Actually, they have two critical fields. So, after first critical field, still you have the superconductivity until you reach the second critical field called X critical 2. So that means the magnetic field can be really high, right? So above that second critical field, you lose the superconductivity. So this is usually this widely seen. So these are standard, we call the type 1 superconductor, niobium, different alloys. So this is for the high Tc superconductors. But you can see even type 1 and type 2, the current density is not very different, right? Yeah. But magnetic field can be really large. You can apply large magnetic field for type 2 superconductors. So if you look at your periodic table, you will see materials that can be superconductors at ambient condition. These ones in blue, these are all superconductors at ambient pressure. But there are some materials, they can be superconducting if you pressurize them. Even iron, recently they found, they can be superconducting under high pressure, otherwise they are not superconducting. But Tc values of these materials are very low. We are talking about below 10 Kelvin. So these are the materials, they can be superconductors, or these blue ones. So green ones can be superconducting under high pressure. But the interesting thing is this iron, typically iron, magnetism and superconductivity, they work in opposite directions. Magnetism is not good for superconductors. So magnetic materials were not supposed to be superconductor until people found iron, that's a good ferromagnet, right? It's superconducting at very low temperature but under high pressure. So also if you look at the critical temperature and the critical field, you can see niobium has about 10 Kelvin. Critical field about 0.2 Tesla. If you consider this one cadmium, your Tc is only 0.6 and Tc Hc is about 3. So we can see all these numbers. So recently they found even lithium to be superconducting, but in millikelvin temperatures. Okay, this is the theory I was trying to explain to you. So you have this Cooper pair, right? So I have the two electrons in the Cooper pair, this one and this one. So when it is passing this way, you can see this electron has velocity in this direction, momentum in k. So the other electron has momentum minus k. So when first electron sees your lattice, you can see this polarizes because it's negative charge and positive ions. So now when the second electron comes, it's already this polarized, the lattice will experience force on the second electron. Second electron is attracted the concentration of these positive charges left behind by the first electron. First electron polarizes that, second electron will be attracted to. That's why, that's what keeps the two electrons together. So, like I said, these are, if you look at your, if you draw your energy diagram, typically we know your electrons are filled up to EF, right? But if you have superconductor, actually you can have your EF in this range by delta, right? So you can have up to, there's a gap here. So above that you don't have any Cooper pairs. So then this is another very controversial theory. Since these electrons, we have two fermions, right? So then when they combine, what do you get? You are getting actually spin 0 or 1. What is 0 or 1? That's basically bosons, right? So if you have a spin 0, we call that singlet state, right? So spin 1 means triplet state, because triplet state you can have up, up, down, down, or the half of this up, down, right? That's the triplet, 3 states. But singlet state you have only up, down, negative, right? Here up, down, positive. Here up, down. That's why this is antisymmetric. These are symmetric, right? The triplet states are all symmetric wave functions. Singlet states are antisymmetric. So that means S equals 0 and S equals 1 means actually we call this is the S wave or P wave. You know the definition, right? So SPEF, typically L equals 0, 1, 2. So we know here what is the total spin? 0, right? That means L equals 1 S wave. Here your total spin is 1. That means you have P state. So see here, there's a controversy whether your superconductivity is due to singlet state or triplet state, or S wave or P wave. So there's more evidence. It should be actually for the conventional superconductor. There's a S wave superconductors, but this new type 2 superconductor, that's more like a D wave. So now, can we estimate the size of the Cooper pair? Like I said, if you have this Cooper pair together, right? We have two electrons. Spins up and down, velocities opposite. So what is the size of this Cooper pair? You can estimate from the Heisenberg uncertainty principle, right? If you take delta E times delta T, it's about H cross, right? That's the, so now if you take energy as a delta, so suppose the size of your Cooper pair is about, say, we call that the correlation length. So then delta T is more like the length divided by your Fermi energy, right? So this is about H cross. So that means your theta is given by almost Vf times H cross divided by your delta. Delta is that energy you require to break the Cooper pairs together. So you can see here, Cooper pair size can be estimated by the Fermi energy times H cross divided by the we call delta as a superconducting gap. Remember, semiconductors have band gap, right? So that's basically your conduction band and valence band, so we call this is Eg. Then the superconductors, remember we had this Cooper pair states. Then we have this delta. After that, this Cooper pair broken into quartz particles, right? So this delta is what we call the superconducting gap. Okay, so here you will see how the superconductivity evolved over the years. Like this is where the first superconductivity was seen for mercury, right? 4.2 Kelvin. This happens in like early 1900. Then they found lead, niobium nitride. So that was pretty exciting. So going from 4 Kelvin to about 20 Kelvin. So then it went to about 40 Kelvin. So then most interesting thing happened in 1984 or 1985. They found superconductivity above liquid nitrogen. Liquid nitrogen temperature is what? 77 Kelvin, right? So until this one was discovered, you needed liquid helium to observe superconductivity, right? That's pretty expensive. But once they found this material, yttrium, barium, copper oxide, we call YbCO. So that's a standard. So when that was discovered, your critical temperature was like 97 Kelvin. That was very exciting, right? Liquid nitrogen. Now we can just pour nitrogen and look at this one. After that, there was a lot of, during this time, everybody was working on superconductors, right? So whole idea was to get this value where? To room temperature, right? So still it hasn't happened. Still there's a hope. So now I think record is something like 200 Kelvin, but under some pressure. A lot of effort. Now that I think effort has kind of gone down now. So that's why that this YbCO actually superconductivity happened. You can see you have these yttrium atoms, then you have barium atoms. Important thing is this copper oxide. Here you have copper, oxygen. These are making two-dimensional planes. This copper oxide in 2D layers. So in between you have yttrium and barium. This is the reason why you have the superconductivity, that two-dimensional copper oxide planes. So like I said, this one has L equals 2 pairing. So that is D wave, right? Not L equals 0. Typical the conventional superconductors have L equals 0. So that is S wave. So this high TC has L equals to, this is D wave. You can see the structure that was very easy to make this one, just ceramic, right? Just take yttrium, barium, copper and just pelletize it and heat it in oxygen environment. So you can easily make the material. Then there are some other still similar structure, copper oxide. Then very recently people found another interesting superconductor called magnesium diboride. So, but that TC is not very high. It's about 40 Kelvin. You can see this becomes superconductor here. But this is something different theory. So this people explain this one. This is how that one looks like. You have boron layers here and magnesium layers. Again, these two-dimensional structures. But here the superconductivity gap coming because of this, the sigma and pi bands. You can see here how they are overlapping with some very small interactions. Okay, so then this how things started. So let me quickly go through. This is where the first thing happened, right? What first thing was liquid helium was made by liquefying helium gas, helium-4. So that has a boiling point of 4 Kelvin. Because of that, they could measure the resistance of mercury, and they found the superconductivity. Then they found this interesting properties of the superconductors. We discussed about this one, right? Magnetization. Then you have your critical temperature and critical fields. Then your this is same thing for different temperatures. So resistance you can have goes to 0. You can see it's not perfectly going to 0, right? There is some fluctuation. So this is interesting. You can see how the resistance and heat capacity changes. Here resistance then goes to 0. Heat capacity, if you look at, it has this linear dependence. Then all of a sudden there's a jump and going down to 0. So this has some exponential behavior. So I don't know whether you guys are doing statistical mechanics. You know difference between phase, the type 1 and type 2 phase transitions? What is the critical phenomena? So typical type 1 superconductors, actually that's a type 1 phase transition. So that's why you see this kind of discontinuity. Your first derivative is discontinuous, but the second derivative can be continuous. So, but if you look at the type 2 superconductor, that's a type 2 phase transition. So that's some details you don't know. Important thing is at TC you can see phase transitions happening, right? Here resistance goes to 0. Here initially linear heat capacity becomes discontinuous. Here it goes to 0. The critical the magnetic field also depends on T. That's how this graph looks like here. So this is then Meissner effect. They found this perfect diamagnetism. So then these London brothers, they came up with this penetration depth thing, right? Magnetic field doesn't go to it's 0, but it goes to 0 with this exponential, the exponential decay, right? So you have this penetration depth delta. There are two important parameters. This one thing is penetration depth. Other one is this correlation length. These two are the most two relevant parameters in superconductors. We'll talk about that one later. Today mostly I talk about this historical development. Then next class we will derive all these equations. So then superfluidity. So something similar phenomenon discovered in 1937 on helium-4 gas. Helium, anybody remember helium-4 versus helium-3? What's the difference? Helium-4 has how many protons and how many neutrons? Helium-4 has 2 protons and 2 neutrons. That is helium-4, right? So then if you take, that means you have 2 electrons, right? 2 electrons, 2 protons and 2 neutrons. If you take helium-3, you have 2 electrons. That's why they are isotopes, right? So here you have 2 protons and only 1 neutron. So that means this has integer spin. This one has half spin, right? So this is basically a boson. This is a fermion. So that's, then if this is a boson, we know that's easy to condense, right? To get to the superfluidity, then Bose-Einstein condensation, all the things. But fermions, later they found even helium-3 can be superfluid. So that we'll talk about later. How can helium-3 become a superfluid? Just like superconductors. Here you have one helium-3 atom that has half spin, right? If you have another helium-3, what happens? Another fermion. If they become together, that can be a boson, right? So this is more like Cooper pair in the superconductor, right? Superconductor also, you have one electron with spin up and spin down and momentum K and momentum minus K. So when they come together, they make a boson, right? It's exactly same phenomena happened, helium-3. Let's talk about that one later, but here, 1937, they found the superfluidity of helium-4. So superfluidity means, just like this one, you have this some density of normal state, some this liquid part normal and also superfluid density. So you can see when you go below your TC, so superfluidity also we have this transition temperature, right? So it's not the same as superconducting transition temperature. We call the superfluidity transition temperature. So you can see above, below when T is less than TC, right? So you can see here T over TC is 0.9. So that means your T is less than TC, right? You can see your the superconducting phase is becoming larger. So the superfluid fraction. How about the normal fraction? That become low, right? Because above the transition temperature, there is no superfluidity phase, right? So everything was normal. But if you go below, you can see your superfluid fraction becomes much higher, become almost all here. So at this point you have both of them, right? But if you go below, much below TC, you can see everything becomes superfluid. So you have no normal fraction of your superfluidity. If you measure your like heat capacity, you will see. So again, just like that, you above TC, you have this. Then you have this first order phase transition happening here. Yeah, that's the order I'm talking about. Phase transition order, first order or second order. That's something we need to understand. Here, that's so. Actually, superfluidity was first observed when that becomes superfluid. Why do we call it superfluid? Any liquid has a viscosity, right? So superfluid means your viscosity is 0. So that means if I have liquid helium, suppose in a tube like this, suppose I have liquid, this helium-4. Suppose this helium-4 is below, above your TC, that means it's not all superfluid, right? But if you cool it down to below TC, there's no viscosity. That means what happens? This liquid can go along this tube without anything, right? Because no viscosity means there's no friction, right? This one just go above this one. Actually, if you have something like this, if you cool this one below TC, you will find a fountain of this helium. Because they just go along this one and making a fountain like that. That's because there's no viscosity for that helium. It can just flow through that one. So this happens around like 2.17 Kelvin. Also, it has no viscosity. It is very difficult to contain that one. Actually, I had, when I was doing my PhD, my experiment was real difficult because I have this, I had the microwave, the resonant cavity. So then my sample was inside that cavity. Then I had to kind of have very tight fitted cap on this one. This was on, I was cooling with liquid helium, right, helium-4. So then when I was taking data as a function of temperature. So as long as I reach this 2.17 Kelvin, if my the seal was not perfect, whole experiment is ruined, because the helium just get into your probe, then whole thing is ruined. Then I have to remove helium and take it out and make it again. You can see immediately when I reach like 2.5 Kelvin, I am so nervous. I don't know what is going to happen. If I can pass 2.17, everything is fine. But several times that happened. The moment when I hit this one, everything is ruined. I see this nice microwave absorption and all these things. At that point, everything is gone. So that's really this. We call that a lambda point. So at that point, everything becomes superfluid. Okay, so like I said, this Landau, Ginsburg, they came up with this real nice theory. So to explain the superconductivity, that time there was no BCS theory. This is only this phenomenological theory. So Landau came up with this one parameter theory. So it's a complex number, psi. So he expressed the Gibbs free energy for the superconducting state with respect to the normal state. The difference between superconducting and normal state Gibbs free energy difference, he wrote in terms of this single parameter. He wrote it like some constant time, that parameter squared, psi is a complex number, plus b over 2 psi to the power of 4. So we will see how he came up with that idea. So if you look at this one, depending on A and B, you can draw this difference between this. So GS minus GN, I call it G bar. If you plot this one, if A is a positive number, it looks like this, right? You can plot and see. If A is a negative number, this function, this one looks like something like this. Because you can see, right, with plus and minus how they look like. So then, because that A is the transition point depends on the sign of this A function. So we'll get back to this theory in the next class. So right now I just want to see how, but this is how Landau initially introduced his theory. Then actually there were certain things he couldn't prove. So then Ginsburg came and added some additional term here that involves magnetic field. So that's how the theory started developing. Yeah. So he introduced this additional term. So in addition to what Ginsburg, the Landau had, he introduced that has this critical field divided by this one. So then the entire theory looks like this, say A psi squared plus B over 2 psi 4. Then you had this plus this BC squared over 2 mu 0, some other terms here. This additional term comes here. I'll show you how I'm going to work on these things later. Then in 1950 they found another interesting property called the isotopic effect. Remember TC, for a given material we think TC is same, right? But they found even the same material, depending on the isotope number. Mercury, you can have different isotopes, right? Your atomic mass can be different, right? Isotope means you have same number of electrons but different number of neutrons, right? Electrons and protons are always the same, right? But depending on the neutrons you can have different. So this is the atomic mass, atomic weight. You can so different mercury with different isotopes. You find your TC is changing, not much but very linear relationship. They found Tc is depending on 1 over square root of this m, the mass, 1 over square root of m. Also the critical field also depend on 1 over square root of the atomic mass. That's also very important phenomena. So actually then the BCS theory, they came up with this, I don't know if they are familiar with this. In StatMat, do you do the Feynman diagrams? Probably not, right? So if you want to, like basically here we are talking about 2 electrons. So one has momentum P1, another one has momentum P2. Then it has a phonon interaction, the phonon energies H cross K. Then this momentum changes to P1 minus H cross P2 H cross. So this is for one electron in the Cooper pair. This is for the other electron. If you know this Feynman diagram, you can write your momentum, energy, and all these things using these Feynman rules. So basically, in real picture is this one, right? You have these 2 electrons which spin up and down because of this lattice polarization. So these electrons can get attracted. So that attraction energy is higher than the repulsive energy of the 2 electrons. Then they become one Cooper pair, right? So then this electron can distort the lattice and move along the lattice. So that's basically electron phonon interaction. So here, this is the basic idea, right? The phonon energy plus Coulomb energy, that should be a negative number, right? That's why it is attractive. So that's the reason. So these are the 3 people, Bardeen, so Schrieffer, Bardeen and Cooper. So here if you think in terms of this Fermi surface, you can see you can have one electron at minus K, other electron is like plus K, above the Fermi energy. So all these things we'll talk about. So everything we discussed, they could derive everything using that the BCS wave function. So that's a very so even all these things we talk about the isotopic effect, then energy gap, even this that penetration depth, all can be derived from writing that right wave function for the that BCS wave function. That's what actually they did. They came up with the right wave function, right? So then you could solve it for energy and everything. So like I said, yeah, you can see how these momenta are. So one has K up, K minus. So but spin also they have opposite momenta, right? So then these are not important. So we also talk about spin singlet and triplet. We know singlet state even functions, because this is the remember we talk about, you have to be careful. Total wave function symmetric means your spin and spatial too, right? So you have to be careful, because psi has spatial dimension and the spin dimension, right? We know spin symmetric or antisymmetric. Then depending on that one, your pi should be. So if the whole wave function is symmetric, if spin is symmetric, then the spatial part should be antisymmetric, right? So you have to be careful what you talk about. Oh, then last thing, then I will stop here. So this 57 Abrikosov, I also met him once. So he found this something called the vortices. That's really interesting with these type 2 superconductors. Remember, you when you have a superconductor, if I have a magnetic field, what happened to the magnetic field? It cannot go through, right? It has to go around. So there's no magnetic field through this one. But Abrikoso found for this type 2 superconductors, there are regions you can have magnetic field coming through. So that means these regions are non-superconducting, right? So these are superconducting, that's why it cannot go through. But there are some regions, they are non-superconducting. We call this the superconducting vortices. You will see magnetic field going through. If you look at your magnetic field, you can see in this given vortex, the magnetic field is penetrating through. That means the superconducting density is 0, right? Because there are no superconductivity here. So that was really interesting. Actually, that's why we call this a dirty superconductor, right? It's not entire thing is superconducting. Regions are non-superconducting. That means if you look at your this curve, this is what for the traditional superconductors, right? But in these ones, you have this one, then there is a region, it doesn't go to 0 immediately like this one. We have area, that's called this H critical point 2. Here this H, there's only one HC. Here this one has HC1 and also HC2. Only after this one it becomes 0. So if you look at your HC, you can see this for the type 1. By the type 2 you have two different superconductors. Here after this one everything is normal, but here you have some mixed state. You have superconducting and non-superconducting, but after that one nothing is superconducting, right? Actually it's real interesting. People look at the magnetic microscopy. So what if you put a sensor and apply magnetic field, what do you see? You will see only regions of this magnets, right? It's a really beautiful experiment. What they did was, you can see how this one, what are these? These are the vortices. These are the ones, they are non-superconducting, right? The magnetic field is coming through these regions, they are superconducting. So that's why magnetic field is not going through. So this is how, from the squid microscope, they look at these vortices. These are real stuff, it's nothing hypothetical, right? Okay, so I will stop here, then we'll talk about some physics behind these things. I just wanted to give you. So one last thing is the Josephson effect. This is also very interesting, the tunneling. So if you have two superconductors, so then if you put an insulator here, so if you bring these together, actually these Cooper pairs, they can tunnel through here. If the your barrier is very thin, you know, simple quantum tunneling, right? If you have two metals or something, if your barrier is very small, electron can tunnel through. That's how the scanning tunneling microscope works, right? Same thing, if you have two superconductors, if you have a very thin barrier, whole Cooper pair can tunnel through. That's what we call the Josephson tunneling. So the Cooper pair tunneling, that has a lot of interest in applications, making world's most sensitive device called the SQUID, superconducting quantum interference device, things like that. Okay, so I'll talk about this one in the next class. So we can finish superconducting in the next class.